today. One never knows whether you really need introducers for people you know so well. Efim has, of course, contributed many, many things to the theory of liquid crystals. And today he's going to tell us about weak crystallization, which is an ancient and very useful theory applied to membranes.
Thank you very much. Indeed, I am very well known among few my relatives and few friends here. Thank you. So needless to say that it's double pleasure and double honor for me to have second seminar here, and perhaps for most of you, you need double tolerance to listen the second time. So it is my title, and I was said, might be it's not the same, precisely the same as announced in the program, I was said that it's grammatically wrong. Because I am not in the position even to discuss English grammar, please feel free yourself, reshuffle the words and the title as you like, with two exceptions, weak Landau theory or Landau weak theory. Because it's not true, it's indeed very powerful theoretical tool, Landau weak crystallization theory. What it is about, weak crystallization theory? It's about crystallization. And everybody knows that standard conventional liquid crystallization is very strong first order phase transition. What does it mean, by the way, strong or weak? There are many criteria how to distinguish strong or weak first order phase transition. Basically, all of those criteria are equivalent. Right now, I will tell one criterion, it's latent heat. If latent heat for first order phase transition per particle is of the order of Kb transition temperature, it means strong first order phase transition. If it is smaller or much smaller, it means weak first order phase transition. So conventional liquids crystallizes by strong first order phase transition. However, pure theoretically it's not forbidden to have weak first order phase transition or even continuous crystallization phase transition. And due to this fact, long ago many famous scientists discussed principal possibility to have almost continuous crystallization phase transition. Just to name a few, I will show one slide about history, not only because I'm like all old guys love to speak about happy pastime, history, but because history, especially history of science, could be quite instructive and useful. So the first name in this list, van der Waals. Soon after his thesis, 1873, he suggested that indeed, like a critical point he found for liquid gas phase transition, could exist something similar for crystallization, for liquid solid phase transition. So it's 19th century. Next person, also equally famous, Max Planck. He tried quite hard to predict theoretically critical point for water crystallization. Even he has published a paper in this year. Now it's in school textbooks. Everybody knows that it's impossible to have critical point for crystal liquid phase transition because both phases have different symmetry, so it's impossible to go continuously from one phase to another. But mistakes of great scientists are not the same as mistakes many of us. They are quite instructive because these two works motivated a lot of investigation, high temperature, high pressure studies, and as a result they discover a lot of very interesting structures, phase transition, so it was quite insightful mistake. Next name to mention, Lindemann, British scientist, who in 1910 published his criterion for melting. Until now, not explained small numerical prefactor in this criterion. And this criterion equally applied to first order, strong first order phase transition and to continuous second order phase transition. By the way, this paper, Lindemann paper this year, was first citation of Einstein paper on vibrations, on Einstein oscillators. For 3 years, Einstein had 0 citation for this paper. Nowadays, it would be very difficult for him to apply for a grant with such publications. 0 citation for 3 years. Next name to mention, Landau. In 1937, he applied his theory of phase transition, second order phase transition, to crystallization. Therefore, assuming that crystallization could be realized as weak first order phase transition. Of course, it's very incomplete list of names, so just only few names to add about unconventional transitions, crystallization transition. It's Berezinski, Kosterlitz, Saulis, who discussed in this in 73 possibility of crystallization via dislocation mechanism. By the way, Feynman, more or less at the same time, also developed such a theory, but never published. In fact, the full number, complete number of his publication, less than 30. I have 4 times more. I don't know whether I should be very proud of this. So what it is about, weak crystallization phase transition? Luckily for me, our chairman just few days ago introduced what could be, in his lecture about open, what could be the order parameter for crystallization. The natural choice of the order parameter is to find some physical or mathematical quantity which distinguish one phase from another. What's the difference between liquid and solid, crystalline solid? In liquid, the density is uniform, just a constant. And in solid, there is density modulation. It was the notion of the order parameter introduced by our chairman a few days ago. My supplementary materials that I've introduced special notation for this order parameter, psi. And besides pure semantic, I've added to stress that it's modulation with characteristic scale of the order atomic scale, short wavelength modulation. And this semantic supplement, in fact, very important. So this is the order parameter for crystallization. I will call it short wavelength order parameter. You will see that it's important. And so in liquid phase, the average value of this guy is 0. In solid phase, it's not 0. And we arrived to a second criterion for weak crystallization. If this guy is the average value of the order of 1, it means that it's strong first order phase transition, strong crystallization. If it's smaller than 1, better to have much smaller than 1, it's weak crystallization phase transition. So the order parameter, and now I assume that this order parameter is somehow small, smaller than unity. Next, we have to expand free energy in terms of this order parameter. Unlike physicists, unlike normal civilized people, very often living in reciprocal space, not in coordinate space. So I will do the same. I will expand the free energy in reciprocal space. Looks like conventional Landau expansion. No linear term. Why no linear term? Because as I define, psi is short wavelength order parameter. It means that it's short wavelength variable. Whereas free energy, it's macroscopical, it's long wavelength. So it's impossible to have linear term. Linear term is forbidden. Next, quadratic, cubic, and fourth order terms. And because it's short wavelength order parameter, the coefficients in this expansion could be essential function of wave vectors. First, they have to satisfy uniformity that f is long wavelength variable. So here it's q and minus q. Here, all 3q has to sum to 0 and so on. It's written here. How this coefficients depends on wave vector, it could be analyzed without any detailed knowledge about microscopic of the phase. Just based on, say, symmetry arguments. So what does it mean in the Landau series that we are approaching to phase transition? It means that coefficients in front of quadratic term should go to 0 or should become smaller and smaller. It means approaching to phase transition. If for conventional long wavelength order parameter, for conventional phase transition, all of us get used to liquid crystals, Q expansion, Q is the order parameter, or in magnetism. What does it mean that coefficients becomes smaller and smaller when we approach into phase transition? It means that it becomes smaller and smaller uniformly over space, or because we are living in reciprocal space, it means that it becomes smaller and smaller in a single point, q equals 0 in reciprocal space. It's conventional long wavelength order parameter, and conventional long wavelength Landau series is coefficient small near a single point. And this fact, trivial fact, it makes life a bit, theoretical life, a bit boring, because what does it mean? When this coefficient is not too small, fluctuations very weak, it means that mean field theory works well, and that's it. If this coefficient is very small, it means that fluctuations are very strong. We have to apply rather heavy machinery of renormalization group, epsilon expansion, and so on. And again, that's it, and nothing in between. On the contrary, for weak crystallization theory, from the symmetry arguments, crystallization is transition from liquid phase. In liquid phase, this modulation vector, as any vector, it has direction and modulus. But direction may not be determined in isotropic phase. Any direction is equivalent. It's isotropic phase. It means that energy may depend only on the modulus of this modulation vector, not on the direction. What I said mathematically means that these coefficients in front of quadratic term, should have the following form: some constant plus this term. It's just requirement of symmetry. Next, if, and we will see that it is the case for weak crystallization theory, only the small region near Q naught is relevant for the behavior, if relevant Q near Q naught only, then this term can be rewritten in this form. It's just identity. It's the same term in these conditions. Similarly, I could analyze dependence on Q, cubic term, fourth order term. It turns out, I skip this, it's quite easy argument, that mu, assuming that weak crystallization is granted, is just a constant. Lambda, in principle, could depend on two angular variables in 3 dimensions, or on one angle in 2 dimensions. Just for the sake of simplicity, I neglect this, the angular dependence of lambda. For my purposes, it's not relevant at all. So I consider mu and lambda as a constant, and only this term, quadratic terms, is Q-dependent. And you see what I said, that here, now I could, first So what does it mean? It means that approaching to phase transition temperature, to weak crystallization phase transition temperature, fluctuation of this parameter, it becomes small when we approach not a single point in reciprocal space, but it's small near the surface, the whole surface, Q equal Q naught. It's in 3-dimensional sphere, in 2-dimensional circle, so it gives the intermediate region of what I mentioned before. So fluctuations, individual fluctuations could be relatively small, but the phase volume for fluctuations is quite big. It's sphere or circle. It's surface or line in reciprocal space. And it gives very specific universal behavior for all quantity for this weak crystallization phase transition. Now with this term I could perform inverse Fourier transformation and write down Landau free energy in real coordinate space. So here it's cubic and fourth order term, and second order terms also quite usual, psi square, but gradient terms it's quite different. It's not like we get use gradient psi square. It's first of all, it's fourth order over gradient, and with this very specific feature. And this very specific feature, it leads to what I said. Fluctuations are soft or important, being individually not too strong, near the big volume in reciprocal space. So it is about weak crystallization theory. In framework of mean field theory, everything is easy. Gradient term, if we are talking about mean field, is not important. And so to analyze all possible structure, I have to expand the order parameter in Fourier series. In principle, if it contains infinite number of terms, certainly it's impossible to analyze structure with infinite number of terms. But luckily, again, if criterion for weak crystallization is granted, among this infinite number of terms, only few harmonics are relevant, and this can be analyzed easily. I will skip this. It's trivial minimization. It just shows the phase diagram for weak crystallization of 3-dimensional liquids. High temperature phase is isotropic, then BCC cubic crystals, then hexagonal lattice of liquid columns, and then 1-dimensional lattice of liquid layers, mectic phase. So it's a bit counterintuitive sequence of phases, but it's counterintuitive if we are thinking about gradual crystallization. But Landau theory, it deals with gradual breaking of symmetry, isotropic phase, closest by symmetry, cubic crystals, and so on and so on.
Then the quartic gradient term change the upper critical dimension?
Yes, indeed, yeah.
But what is the upper critical dimension?
You mean when this hard I will formulate. It's just in you mean when this not mean field, but this Hartree approximation applicable? I will formulate. If not, we have to go. So it was mean field. Now fluctuations. Fluctuations, to describe fluctuations, because fluctuations means that something non-uniform, I have to include the gradient term. I have to I have to calculate correlation function. And bare correlation function, just without fluctuation from harmonic energy. Bare correlation function can be found from this term, from this term, this term. It has trivial form. Like Arnstein-Cernik, it's proportional bare correlation function of the order parameter. It's proportional to 1 tau plus q minus q naught square, with certain coefficients here. It's like Arnstein-Cernik, but here it's q minus q naught. It's soft or easy excitable near the sphere or circle. It's back relation function. And fluctuations, the only role of fluctuations, if decrystallization assumption are granted, the only role of this fluctuation is renormalization of this parameter tau. Instead of this tau, we have certain parameter, certain variable delta, and we have to find this delta. For this delta, one can derive the explicit equation. It reads like it's shown here. And here, I've shown the criterion for weak crystallization, which I will be using what follow, which is equivalent to what I said before, semi-qualitative. Small latent heat or small value of psi average. This renormalized delta should be smaller than this combination. B, its coefficients in front of gradient term, this unusual gradient term. And Q naught is the main harmonic of density modulation. This is about fluctuations of the order parameter. And so theory applicable when I could consider only renormalization of delta and neglect renormalization of vertex parts and all other coefficients. And now my aim to apply this weak crystallization machinery to describe so-called main phase transition in membranes. So I will repeat essentially what I said before, like in old Soviet time anecdote. I've heard from Dima Khmelnytsky, who is here, because he is in Cambridge, it's not dangerous to cite this anti-Soviet anecdote to a person. So anecdote about how one guy came to a policeman in Moscow in Red Square and told him, "Comrade policeman, good morning, I'd like to tell you anti-communist anecdote." And policeman responded, "Are you crazy? I am policeman at my duty at Red Square." "Don't worry, Mr. Comrade policeman, sorry. I will speak slowly, repeat my joke 2 times. So I'm repeating again what I said, but in application to membranes. So what are membranes? I think everybody knows. Membranes omnipresent in any biological systems. And in all membranes, there is still debating phase transition. It's called main phase transition. It means semantically that it's something important. Debating, I mean that the nature of the phases is not very well known. And debated, I mean that even the characteristics of these transitions are not very well known. So it's just a cartoon of membranes. It's biological. The transition occurs in biological membranes. It occurs also in artificial single lipid membranes. It occurs in a single bilayer. It occurs in multi-stack of membranes. So it's indeed a very general feature, this main phase transition. As I said, membranes are omnipresent. In the human body, the total area of all membranes is 200 kilometers square. It's a typical size of new Russian oligarch secondary residence, dacha in Russian. So it's enormous, the size of the membrane inside of us. And in each of these membranes, there is this main phase transition with quite unusual feature. It's well-studied experiment. There are many, well-studied, it's exaggeration. There are many experimental studies of these phase transitions. So the main phase transition, they call transition from liquid, fluid phase to gel phase. What is the nature of gel phase is not well established. Some people claim that it's crystalline, but bad crystals, mosaic or polycrystalline crystals. Some people claim that it's gel in our conventional understanding what is gel, something entangled. So it's still debated in the literature. What is the fluid phase is known. Phase diagrams. In phase diagrams, so this transition to gel phase, main transition, it occurs, but very often, not always, but very often, not far from this transition, not far, I mean in phase space, not far from this transition, there is another transition to ripple phase. Ripple phase, it's transition when the shape of the membrane undulating within the plane. But not always, very often, but not always. What is the specific feature of this phase transition, main phase transition, found experimentally? First, it's first order phase transition. There is latent heat, all features of first order phase transition. But second, it's first order phase transition accompanied by quite noticeable, experimentally visible fluctuational phenomena in many, say, experimentally measurable properties. And besides this fluctuational phenomena, fluctuational correction or contribution, they could be described more or less semi-quantitatively by quite large critical exponents. Typical standard long wavelengths phase transition, usually, for example, for specific heat, it's quite small fluctuational scaling critical exponent. And here it's about one or one bigger than one even. And this suggests that maybe it has something to do with weak crystallization phase transition, because weak crystallization phase transition has the same feature, first order nature and fluctuation. I should stress that it's not necessary has something to do with crystallization, because what we need to have this technology and to have this behavior, it's not crystallization. The only things we need that there is large phase volume where fluctuations are easily excitable or soft. The only things we need. We need high temperature isotropic phase, it's the case for membranes, and we need this large phase volume of fluctuations where fluctuations are soft. It's not necessary crystallization, it could be rippling, it could be dipole order, ferroelectric ordering with domain structure, it could be something else. The beauty and the power of this kind of Landau approach, that in fact it's not mandatory to know microscopical construction of the phase. I could base the theory and predict some measurable property based on symmetry arguments, and that's it what I need. In fact, Landau did the same for superconductivity. At that time, without any knowledge of Cooper pairs in this phenomena, he, together with Ginzburg, predicted all experimentally measurable properties of superconductors. So it's what I'm...
You seem to be implying the critical exponents are different approaching from the high temperature phase or from the low temperature.
Right.
Is that right?
Yeah.
Very different.
Okay, it could be very different, it could be not very different. It depends, you will see. It depends on ratio. The parameters which determine behavior, it's delta. It's renormalized stiffness of the fluctuations. It could be very different in both phases. In this case, I could expect very different behavior, very different. It could be not very different in both phases. But I have some universal relations between delta and other property. So it's randomly selected experimental data just for illustration. Don't pay much attention to these pictures. In fact, there are huge number of experimental papers. Unfortunately, all of those not very high quality, I would say. But qualitatively, what they say is more or less undisputable. There is, say, semi-critical behavior or quasi-critical behavior for specific heat with quite large critical exponent of the order of 1.5. Here, I've shown spacing. So what I am discussing is phase transition within single membrane. But if there is stack of membrane, and if something happens in one membrane, certainly stacking also will be affected. And this is also observed. It's a repetition distance and smectic A-like multi-layer stacking of membranes. Also could be called pseudocritical behavior.
Is that experimental system?
It's different kind of, it's observed, as I told, almost in all kind of membranes. So its transition temperature could be different, but behavior it's more or less always like this.
The experimental system is under tension?
No, it's just single membrane. Here it's just smectic-like structure, here for this data. And this is Bragg reflection in direction orthogonal to smectics.
But the single fluid membrane is unstable. I mean,
okay, it depends. Here, as I told, it's not single fluid membrane.
it's a stack.
It should be on substrate or something. Here it's multi-stack and repetition distance.
But that gives it some kind of tension. I mean,
Okay, you mean mechanical. It should be frame. How it measure your questions? It should be how to measure specific heat. Again, specific heat mainly measured in multi-stack, not in.
Stacks of membranes form nice lamellar phases. in the staple.
stacks are okay. I was talking about a single.
Probably what he's talking about.
It's stack of membranes, yeah. It's like smectic.
A single fluid membrane.
Okay, my point is that phase transition occurs in a single membrane. But if something happens within the single membranes, something happens in multi-stack interaction.
But for the single membrane, you need something to stabilize it. Single fluid membrane can have.
Okay, no
A single
problem.
membrane in a stack can undergo an in-plane
No problem. No
ordering
problem.
transition.
Yeah. Or I could speak about, you are talking about single flat membrane. I could think about giant vesicles or giant micelles. It's huge object. It's stable by itself. I could measure, and the curvature is so small that it's basically flat. It's not a problem.
Not the fluid.
I will show fluid and fluid phase. I will show this data. Just skip few. This data is viscosity, internal viscosity. It's measured mechanically.
Okay, we can.
Just moving a small ball around the huge vesicle or huge bilayer micelle.
With the surface tension, do you have surface tension?
Surface tension could be also estimated, but here is viscosity. It's mechanical. It's a dynamical experiment.
In a stack, the surface tension is subtle.
No, he's
You
not-
have negative tension pulling it in.
No, I'm
and
not
collisions
talking about
which are
stack.
stabilized.
I wasn't talking about.
Okay, here I'm this experiment performed on single spherical but huge. It's micron size. It's macroscopical object, and you could measure viscosity. Okay, you see viscosity. It's internal viscosity for single membranes, and you see how it changes. First, 2 order of magnitude, 100 times. It's real critical behavior. And the exponent here is 1.5. So here is a sort of summary of semi-qualitative summary of experimental data. There is first order phase transition. They claim, all experimentalists claim this, main phase transition. And there is critical behavior for specific heat, for viscosity, for relaxation time, for sound velocity, with specific cusp-like anomaly for sound velocity, for bending modulus, and with quite large critical or pseudo-critical exponents. And what I'm claiming that in the framework of weak crystallization theory, we could, if not explain, not describe, but at least rationalize this behavior, combination of first order phase transition and critical or pseudo-critical velocity. So I'm repeating indeed precisely what I said before, the same energy now explicitly written in 2 dimensions. And I have to, what is the nature of psi? Just for the sake of concreteness, I suppose that psi has something to do with rippling. So psi is a sort of curvature, spontaneous curvature of membrane. I need it only for one thing, that just for simplicity, it means that psi and minus psi is equivalent. But if it's not the case, not a problem to apply the same to any other microscopical kind of weak crystallization transition. So there is weak crystallization transition somewhere not too far in phase space from the main phase transition. And I have to couple this guy with something which characterizes this main phase transition. I don't know what the nature of this main phase transition. Again, just for simplicity, for illustration, I suppose that there is scalar variable phi. For example, its density, because at the main phase transition there is jump of density. Gel phase is denser than liquid phase. So this is phi is the, say, in quotation mark, the order parameter for the main phase transition. I suppose just for simplicity that it is scalar, but I could apply the same machinery for another symmetry of this field. And I have to couple this guy with psi. And that's the end of the story. I will do it. So because psi, I suppose, it's my assumption, but again, it's not mandatory, I could do it, that psi and minus psi is equivalent, so there is coupling phi times psi square only psi square, because psi and minus psi is equivalent. And I added also some function which describe energy of this variable phi. It's not expansion, it's not Landau free energy, it's some function. Phi is not small, I may not expand something. But I need not know explicit form of this function. The only things I need in what follows that this function behaves, say, regularly at phi equals 0. So no singularity, no branching points, just regular behavior at phi equals 0. So I have to work with this energy. It's the same procedure. So to take into account fluctuations, I have to renormalize the coefficients in front of this quadratic term. The equation for the gap for the renormalized is like this. Now there is phi here. Because I am interested in the main phase transition in the part related to phi, I have to integrate out this weak crystallization degrees of freedom, psi. Formally, it's like this, so I have to work with this energy. Formally, it's like this. Of course, I am not able to perform this integration explicitly because there is fourth order term, but I need not this. I have to, I can calculate this derivative. A capital here is the area of membrane. I have to calculate this derivative, and this is explicit expression which is exact in the approximation of weak, which is exact if assumption of weak crystallization is granted. And the structure of phases, the own property of phases is determined by minimization by the condition that this guy is equal 0. Derivative is equal 0. Again, in principle, from this equation, I can calculate, in principle, this functional, as a function of phi. In practice, I am not able to do it, but I can calculate the difference of, it has, first of all, it has meaning, this phi, only in gel phase or in liquid phase. It has no meaning for arbitrary phi. But I can just calculate the difference of this function for gel phase and liquid phase. Again, I don't know about microscopical construction. I know almost nothing. The only things I know that there is scalar variable and couples to another variable which follows weak crystallization transitions. So it's calculation, it's direct calculation from the previous slide. It contains this unknown function. And with this in hand, I can investigate everything what I'd like. So in certain sense, it's the answer. And now, indeed, what Mark mentioned, I need to proceed further, I need to assume something. For example, I've assumed that in liquid phase, delta 1 is larger than in gel phase. And on the contrary, phi, the density or thickness, in gel phase, phi 2, is larger than in liquid phase. It sounds for me natural, but it's not mandatory for the theory. Theory applicable for any relation between the both. So then, under this assumption, I could simplify these equations, and at the end of the simple algebra, I came to the following equations. Again, I know almost nothing here. I don't know phi 2, I don't know this function, I know only that there is reduced temperature tau, and there is this lambda, its coefficient in Landau free energy. And I have to solve these equations. Of course, without explicit form for f, I cannot do it, but I can analyze in two limits, when lambda is large or lambda is very small. Because if lambda is large, from this equation I will find, so that, okay, I will show next slide better. So it's the same equation for these conditions, written for these conditions. This is the equation I have to solve. As a result, I will find transition temperature, first of all, for the main phase transition. As a result of this solution, I will find transition temperature. For the main, it's reduced units, that's why it's tau, not T. So if this guy T naught is larger than 0, it means that main phase transition is above weak crystallization or rippling first transition. It means that both phases, liquid and gel phase, they are above this hidden first order phase transition. I don't see this first order phase transition. It's below of the game I'm interested in. But fluctuations, remember about this hidden phase transition, and it's like this. So it could be tau naught larger than 0. In this case, this is just above the crystallization transition. If tau naught smaller than 0, it means that first transition is weak crystallization, and then I have to take into account, I have to modify a bit these equations, but it's doable, and I will find how it behaves in opposite case. And the both cases could be distinguished if it's written here. If lambda is small, look, I have to solve this equation. If lambda is small, it means that it equivalent just this function equal to 0. I have to find solution this function equal to 0. And in principle, both situations are possible. Phi 2 could be positive, phi 2 solution of this algebraic or transcendental equation could be either negative or positive. In this case, the both situations are possible. So I have to solve this equation. The both situations are possible. So main phase transition above weak crystallization or below weak crystallization. In the opposite case, if lambda is very large, it means that equations I considered before, this equation, if lambda is very, very large, it means that this derivative should be 0. Or more precisely, should be, you could estimate, inversely proportional to square root of lambda. It's written here. And analyzing the previous equations for the gap, so if this guy is very large, I could forget about this guy, and this guy should be positive. It means that for large lambda, tau naught is always negative, and therefore for large lambda, in all situations, first transition it's ripple phase transition. So it's about phase diagram, and I can repeat that I did not use any property of microscopical property. I did not assume any specific microscopical construction. So now about fluctuations. To describe fluctuations, I have to couple this hidden or not hidden average value could be 0 or not 0, but I have to couple this psi to variable describing properties I'm interested in for specific heat, because coupling proportional to psi square and energy is just psi square, it's like this. So very large exponent for the specific heat. It's prediction of weak crystallization theory, irrespective to the fact that no crystallization at all, and might be the both phases are above phase transition. So, coupling to bending elasticity. If I couple this to displacement of the membrane in the orthogonal direction, I will find critical behavior for bending modulus. It's like this. A bit more algebra requires to couple these fluctuations to dynamical behavior, but it's doable. It's beyond the topic of this seminar, and I will find that its behavior scales like delta in this power 3/2. It's compatible with the experiment I've shown you before.
So for the bending, you have a something like
Cusp-like.
del squared h term coupled to psi.
Yes. It's I assume that psi is something like spontaneous curvature, so it means that it's a coupling like this. Yes. So what else? I can calculate structure factor within the layer. Again, it behaves like this. For small q, it's 1 over delta 3/2, because for small q I could neglect this, and for q of the order of q naught over 2, it's quite peculiar behavior. And what I said, that all this, I would not say predictions, all these consequences of weak crystallization compatible with the experiment, not in dramatic, I would say more modestly, not in dramatical contrast with experimental data. I think I will skip some optional slides because it's the minimal model. In principle, I could add to the model orientational ordering related to tails. I could add also some mosaicity within the player. Everything, if needed, could be done, but the price more and more unknown phenomenological parameters. And here it's a sort of minimal model to combine two unusual features: first order phase transition and noticeable fluctuations. Thank you very much.
Questions?
You don't have a diverging correlation link, is that right? Or do you?
No, it's first order phase. It's always first order phase transition. No divergency, but there are quite long fluctuational tails.
So the Q naught that appears there is that sort of the ripple wavelength, or is it really?
If I am thinking about decrystallization phase transition as rippling, it's ripple wavelength. It's of the order of 10 or might be bigger membrane thickness in experiment, I mean.
So are you thinking of ripple phases, or are you thinking something more general?
In this approach, I am thinking about something like ripple phase.
So that means that there should be a signature somewhere in the experiment of what Q naught is.
Yes. It's my point. Yeah, it's my point. Yeah.
And the scaling of the viscosity, does that correspond with anything that people see?
Precisely, it's just viscosity is the best experimental confirmation again. It's too strong. Look, it's fitting. It's written in the paper. It's 2008 seems to me paper. Dimova and collaborate. It's Bulgarian group quite active in this measurements of viscosity. It's 1.5 the exponent. And look, it's from 24 to 22. It's 2 order of magnitude.
This viscosity you mentioned. So
It's two-dimensional. It's internal viscosity.
is this
It's shear viscosity. It's shear
in
viscosity.
the 2 layers?
It's yeah. It's okay. It's
Layer, isn't it?
okay. It's no. It's not shifting one layer with respect to other. It's viscosity of the component creating the membrane. It's two-dimensional system.
What about dilation viscosity?
Okay, it's
Dilation.
yeah. I understand what I don't know. Okay, it could be analyzed within the same approach, but first, no experimental data concerning how it behaves approaching to the main phase transition, and second, it's not yet done. I found this data, and surprisingly, it's precisely what weak crystallization theory could predict. The same exponent. Of course, it doesn't mean that it's true what I said, but.
And what happens to the thickness through the transition? Your other variable. The thickness field.
Thickness behave like a phi. It becomes smaller, and so it's a sort of cusp-like behavior. It becomes smaller when we're approaching from high temperature phase. It's scalar field phi.
Right.
In fact, I had in mind just thickness or density. It behaves similarly. Thank you.